Hi everyone, coming back to our new topic which is positional encoding. Now, what is positional encoding? But before we go there, we'll just quickly understand and recap what we have learned. So, by far now we have understood what tokenization is, we have understood what embedding is. So, tokenization is to basically convert a word into a numerical representation, and then embedding is to basically combine meaning into those numerical representations, so basically converting into embedding vectors. For example, a word play gets converted into a number which is 16, so this is our token provided by tokenization method, and then embedding gives us a 512 dimension vector, which basically is a numerical or vectorial representation of the same word play with the meaning. So now we have a meaning plus vector representation which could be read by computers. Okay, moving forward on, now we want to capture the position of the word, because the moment the position changes in a word, the meaning of the word also changes. So let's, for example, consider one sequence. uh, let's just say we play badminton. So for example, there's a sentence called we play badminton. For now, I'm just considering word-based tokenization so that it becomes easy for us to go through. Now, if it was written play badminton v, it would not make sense. And sometimes the meaning goes otherwise as well. So we don't know what the meaning of a sentence is unless it's in a correct order. So to maintain the order of the complete sentence into a numerical representation, what we do is positional encoding. Now let's say we could have said 1, 2, 3. So the positions of V is 1, play is 2, and badminton is 3. We could have done this as well. And this one is the naive approach, right? Like the very base, like the base approach anyone could think of. Okay, let me just say 1, 2, 3. But what happens is usually we have huge amount of text data. There's a problem with this approach. The problem is it treats these positions as numerical values, which could imply order of importance based on magnitude. For example, a machine might interpret three as bigger number because the magnitude is more, and then hence it might give badminton more importance than the other two words, which is wrong, which is what we don't want in a positional encoding. We just want to maintain the order, and this could lead to biases on how model might interpret the sequence. So the best way to solve this problem is basically normalization. So let's say if I normalize this, for example, 1, 2, 3 becomes 1 by 3, 2 by 3, 3 by 3. This approach is normalizing on the naive approach, like apply a normalization which solves the problem of the magnitude. So the now the magnitude is not much bigger than any of what we think. But this introduces a new challenge. This generates a new challenge for the machine learning to understand this, which basically means if the sentence length is longer versus the other sentence, 0.3 for example might be at fifth position in one sequence, and the same 0.3 could be at 12th position for some sequence. So now the same value is in on different position, which basically implies that positional values changes based on the sequence length, which is again another problem. So what do we do now? So the next approach is basically, just instead of representing by direct numbers or normalized numbers, let's just represent into, it's it's how everything works. Like you basically define with numbers and then you go to uh, going in depth on the solution to generate a solution which solves the problem. So okay, I'll just represent this as a binary representation. Okay, for example, we play badminton is 0 0 0 1 1 0. Okay, so 0 0 0 1 1 0 is now a representation of the same is kind of representing that, okay, 0 0 is a binarical representation for v, 0 1 is the position for play, 1 0 is for badminton. Now the problem with this approach is this solves the problem that we had earlier, that the same magnitude will not be repeated, but this introduces discontinuity. There's a lot of discontinuity. It's not continuous values. 0 to 1, which is a very big jump, right? It just reversed. 0 is reversed to 1 and 1 is reversed to 0. So it's a big jump from, for example, from 0 to 1 here and 0 to 1 here. It's a big jump, right? Now, because it's a big jump and it's discontinuous, we usually ignore it, and also this becomes a little more tedious to keep it binary. So we want a solution which should have continuous, should not judge based on the magnitude as well, and should not be discontinuous. Same value positions should not occur. So okay, now the solution is, let's go into trigonometry and let's say we'll take sine curves, sinusoidal curves. Now the problem with sine curves, okay, basically we'll just see first. This solves the problem for us basically like that. Now it's continuous. Okay, we play badminton, we could come here, play could come here, badminton could come here. Okay, now what if our sequence is bigger? So again, some words come here, some here, some here, but again there is a problem of same magnitude at different position, which is again a problem. So now at this position, the first word and, for example, 1 2 3 4 5 6 7th word are having same magnitude, same y value. First y is equal to 7th y, which is again a problem because we have same magnitude. So now how do we solve this? This introduces again duplicate positions, which is wrong. So the idea was, okay, what we will do is let there be one sinusoidal curve. Okay, and because we have vectorial representation for every bit, for every in a complete 512 dimensional vector, for every dimension we'll introduce one one sinusoidal curve. Okay, for every dimension will produce one sinusoidal curve. So now every dimension is in a different tone. Okay, for example, we could understand this as different amount of intensity is given on every word when we say it. For example, we play badminton, or for example, if I'm angry and I'll be stressing on one specific word, like get this work done. Okay, so I've given a more stress on the word work. Okay, But because I gave more stress on the word work, how would I capture it? Now this solves that problem, because now every word, for example, has is been divided into 512 dimensions. So now every dimension is given a different frequency, right? uh, which solves the problem of same values for different position, right? And that's it. So it solves this problem now. So now this word will be here, the other word could be on this one, the other word could be at the same place but for a different frequency. So if I divide this, these are basically different frequencies. There's one, this one, which is the base one. Then the other one is this. The other one could be more frequent. So yeah, this kind of wavelengths, these uh, positional encoding is divided into. So now the formula becomes a little different. For example, the word we sentence we play badminton is basically a 512 dimensional, 512 dimension for play, 512 dimension for badminton. Okay, now I'll just represent it in this order. For example, we play badminton. Right, we play badminton is are these three sentences. For the first one, I'm taking first one for example. That would be for the first wavelength. I'm just zooming in this one, these sections. What we do is this one becomes like that, and let me just do it by a different color. Okay, now the other one becomes in a different frequency, the other one comes out in a different more frequency, third one is again different frequency, like that. So now every dimension in a word is of different frequency. To define this formula is to define this complete positional encoding, what we do is positional encoding for position at even place is sine of position of 1000 to the power 2i by total number of dimensions, which is 512. I is this position, I is equal to 1, I is equal to 2, 0, 1, I is equal to 2, like that. I is equal to 512. Okay, so I goes till 512. D is for now 512. This 100,000 is called the magic number. There's no concept why it's 1000, is just called magic number because this suits and everything. Now for every position which is an odd number, the encoding for that positional encoding is defined as cos position of that word divided by 1000 to the power 2i by dm. So that's just sine versus cos. So for every even position will take sine, for every odd position will take cos, and that's it. So this is how positional encoding works. This is how we'll do positional encoding.